can see the vector. All right. So if you see our, so I'm answering the question that instead of having a delay element, can't be pipeline the vector multiplier, right? So if you look at our vector multiplier add, so you can see that it has a delay of 1 clock cycle, right? Why? Because we are doing this, okay? So in 1 clock cycle, right? So the output is registered. So we are basically multiplying these things. And then over here, we have one register block where we register these things, right? Yeah. So, and the latency is 1 here, right? So you can actually have like wherever you want. So if you, for example, over here, you can have, a register to between these two, or like, for the, in the output of these two, you can have a register, or else like, each of these you can have it registered, or you can have like multiple registers and let the tool do retiming. You can do whatever you want. But then at the end of the day, this whole module will have, I'm assuming that you're going to have like a certain latency, a fixed latency, right? So even if the latency is not fixed, you can handle that. But for the sake of simplicity, I'm assuming that you have a fixed latency of L, okay, L number of clock cycles. So you get an input, and after L number of clock cycles, you get the corresponding output, right? So here the latency is 1, right? Why we have one register, and like we are basically everything else is combinational. We are combinational doing stuff and then writing it to a register. So you have only one clock cycle latency, right? So now because of this, in the next slide, when you convert this into access stream, and basically over here we are putting this valid. We are basically giving 1 clock cycle latency for the valid as well, right? So that way, like, the valid will match, the invalid will match M data, right? So M data is basically 1 clock cycle delayed from the input. So similarly, the M valid also will be 1 clock cycle delayed from the input. So you basically delay it equally. So if the vector multiplier has a latency of L, then you basically, this delay element also will have a latency of L. Okay. So you can do this latency wherever, however you want. You can have retime it inside the multiplier, or you do pipelining inside the multiplier. So you do whatever you want, but then at the end you have certain latency, right? So then the question is, okay, what happens if you don't have a deterministic latency, right? So so I have some designs where you don't have a deterministic latency. So then what you do is you do this thing inside the module itself. So in the module, you are calculating the output in a certain way. And as you calculate the output, you also calculate when it's going to be valid. Okay, accordingly, right? So basically, so the whole point is this M data and M valid should match. So the M valid should be high when the M data is valid. So that's pretty obvious, right? So how do you do that? So if you have a fixed latency, you can just delay it by a fixed latency. Otherwise, you generate the invalid the same way you generate it. Okay. Any other questions? Is this a common good practice to write an access stream wrapper to a vector MAC instead of embedding the access stream inside the vector MAC? So, it depends on your design. So if your design has a fixed latency, then I would say you can do this because it's very easy to do this if your design has a fixed latency. And I don't think you will have any sort of like a performance impact because the tool can move the registers, right? So if you enable retiming in the tool, then the tool can actually move the registers inside. So like basically it can do stuff like that. Okay. So, and I think like doing like this will keep your code clean. And it depends on what kind of stuff you are doing. So like, for example, your parallel to serial converter. Now, because it's very straightforward and because like you can simply generate the valid and ready from the state machine itself. You already have a state machine, right? So, and because you have a state machine and everything, you can put all this logic inside your module, right? But in this case, this vector multiplier is basically a pipeline. Okay, a pipeline of latency 1. So I'm keeping it simple, right? So it's a pipeline of latency 1. And it's a data pipeline. It takes data and processes something and gives output. So because of that, we don't want to complicate that data pipeline by adding this logic unnecessarily. So you can keep this logic outside. But the tool will basically flatten the hierarchy, move stuff inside. It will do all those things. Okay. Any other questions? Okay. So if there are no more questions, I can move on to the next one. So yeah. So basically, I guess you understood the idea of skid buffer. So, and once again, you don't have to write the skid buffer yourself. It's a good exercise. But then if you're actually making a design, you can take somebody's skid buffer and put in your design, right? So that is all like SoC design is about, like people taking other people's IPs and using it, right? So yeah. And all right. So the next one is basically XC protocol. So full XC. So we are going to talk about like introduce like why like I mean full XC is designed that way and like basically stuff like that. Okay. So for that, I mean full XC is a memory mapped protocol, right? So that means like you have actually memory signals. So you have read like you are reading and writing to memory. Okay. So you have addresses and all of that. So, like then to build towards XE, we will start with the simplest possible memory protocol, and from there we will gradually like see why like different things in XE are necessary, right? So now the simplest memory protocol is SRAM, right? Like the very simple one. So this is actually, I mean, very common in the sense that you will find this in all the SRAM IPs. So like in Xilinx, like I mean, you will get from the DRAM from Xilinx. So like in Vivado, if you like include a IP, this BRAM IP, then it will behave something similar to this. And similarly, if you take SRAM module from a PDK, right? So TSMC, like or else like ARM memory compiler, if you generate a SRAM module for ASIC, then it usually behaves this way, right? So yeah. So the way this works is basically like this. That is like, I mean, if you want to write something, right? So then whoever, I mean, the SRAM is always a subordinate, right? So it's always a subordinate. So which means it responds to request. It will never generate request. So a manager generates request and a subordinate responds to request, right? So an SRAM is always a subordinate. So right. So let's say a manager, let's say a CPU, right? A CPU wants to write into SRAM. So what does it do? It basically sets the write enable to 1, okay? And it sets like the address in the same clock cycle, okay? And then and it will give the data also, right? So it will do all these three things in the same clock cycle, right? It sets the write enable to 1, address, and the data. And in the next clock cycle, the SRAM will update the corresponding position, right? So for the in the particular address, it will put the data, right? So yeah, and then the data will be available in the next clock cycle. Okay, so you have usually one latency, and in different modules you can actually change the latency also. Like so in Xilinx VRAM you can actually set it to the latency 1, 2, 3 like that. Okay, so you can add registers in various stages. But yeah, that's the general idea. And then like I mean, if you want to read from this RAM, what do you do? The CPU sets like say the write enable to 0, and you say like address. You give the address in the same clock cycle and the subordinate will give you the D out. So that is the data in the next cycle, right? So you always know that data is going to come in the next cycle, right? So here is like a quick example of this read and write, how it's happening. So you can see in over here, it's yeah. So you can see this is a read, it's a write transaction, right? So the CPU is asking to write, and it gives an address and a data. Okay. So and this data will get copied inside, okay, into the RAM. And similarly, this is another write transaction, and this is another write transaction. Okay, so you are doing 3 writes to address A1, A2, and A3, right? So after that, now you are like doing read transaction. So when you are doing read, you set this to like 1 0 write enable, and you have an address A1, and you have the data coming 1 hour, 1 clock cycle data. So this is the data that you wrote here. The same data comes out in 1 clock cycle later. And similarly, this data comes 1 clock cycle later, and this data comes 1 clock cycle later, right? So yeah, so this way basically what this is the very simple SRAM protocol. So this is, I mean, what this is what you would do like if you are like writing something. And generally, like I mean, when you have register files inside CPU, we do this. Okay, so it's like a very common thing, right? And very clear. So now from this, like let's build towards Xe. So yeah. So now an actually light subordinate, you can think of it as a just like an SRAM. Okay, it is usually an SRAM. So like SRAM is a subordinate, and basically, so the in like in the general SoC design, like I mean, the idea is like you have memory mapped interfaces. So basically, the way you talk to somebody, way you talk to an IP, is basically through these memory mapped interfaces. So basically, you treat everything like a memory subordinate, right? So you like to anything you just give an address and you give some data or whatever, and that way you can write into different register banks inside different subordinates. So you do that, right? So you can consider any subordinate as an SRAM, okay, for the sake of simplicity, right? So like basically any subordinate behaves like a memory, right? So that's why we say it like memory mapped. Okay, so let's see how that works. So now let's compare this SRAM and an AXI subordinate. Okay, so the Accelerate subordinate has this A clock, A reset n. So these are like from like the spec. And so similarly, you have this address, read address. Okay, so you can see like this has what yeah. So this is AR read address, and then you have R data is the read data that goes out that is similar to D out. Okay, so the address data, and then you have data that goes in that is W data. Okay, that is D in. And similarly, like you have write enable or write, like I mean, you do like that thing that is basically the W valid. So you have like some corresponding signals. But then let's see the differences. Okay, so now like these are some like limitations in our normal SRAM protocol, right? So let's see how actually solves those limitations. So by solving that, like you also introduce a lot of complexity. So that is why like the XC protocol looks pretty complex, right? So first of all, you want to read and write the same cycle, right? So you want to sort of like do these two things parallelly. So which means you can't use single address channel. You need to have separate address channels. So here you have a read address channel and you have a write address channel. So two, okay. And the next one, you read like I mean, in general, you basically in the SRAM protocol, whenever W enable is 0, you read, right? So the idea is like I mean, like the write enable is 1, you write, and write enable is 0, you basically read, right? So that is in a simple SRAM, but that is sort of wasteful, right? So especially if this is a more complex subordinate, then like it whenever the write enable has to be either 0 or 1. So whenever it's 0, it has to sort of like fetch the data and give you. Okay, so we don't want that. So to avoid that, you have like a separate like read request. You have an AR valid. Okay, so if you want to like read something, then you set this AR valid high, right? So this means now if AR valid and AR address, if you put some address in AR address, and if you set the AR valid high, then that means you want what you want to write something. You want to read something. Okay, so that is the read request. So these two basically form the read request channel. Okay, so like I mean the basic read request. The channel has most of. Okay, so similarly you have write request, right? So for the write request you need to have like AW valid. Okay. So if you want to write something, you put basically the what some address over here, and you set the AW valid high. If you want to read something, you put the address over here and you set the AR valid high. Okay. All right. So next one, for the write request, so you can't provide the data and the address in the same cycle. Okay. So now, like in our SRAM protocol, you have to give your address and you have to give your data in the same clock cycle to write it, right? So now, what if you can't do that? Okay, so you can't assume like everyone can do that. All the IPs can do that. So what if you cannot do that? And there's like a good reason why you can't. I will tell that in a minute. But assume like the general case, if you can't do it, what do you do? So now you basically use separate channel for address and for data, right? So that's why you have a AW address, AW valid over here. So this is the address channel and this is the data channel, right? So the idea is basically you can give the address first, and like after some clock cycles, you can give the data to be written. Or else sometimes you can give the data first and you can give the address later to be written. Okay, you can do either one of those. Okay, right. So next one, you want fixed latency. So like the previous one, this is like the biggest problem, right? So in the previous one, you had a fixed latency to read. So you in SRAM, you know that the data is going to come out in one clock cycle, usually. Or else like if you configure it to be 2 clock or 3 clock, you know it's going to come in 2 clock or 3 clock, right? And then like your digital logic, you have to write it accordingly. So you have to know that, I mean, you have requested now, and in 2 cycles, the data will be valid if you set it to 2, right? So, and you have to handle all of that. So now this is not very good if you want to generalize this to a ton of different kinds of subordinates, right? Why? Because like, I mean, then everyone has to sort of adhere to one clock latency, and that is not possible because like you need pipelining and you need to, I mean, sometimes you need more than 1 clock to do some work. So, I mean, yeah. So like you need to have this variable latency, right? So how do you allow variable latency? So for that, the subordinate can respond whenever it wants, right? So, and that is the R value, right? So the idea is this read data, like you send a read request over here. You send a read request. So you put the address and you put the R value high. So now you are asking, okay, I want the data from this address. So that is a read request. And then the subordinate can take its time, maybe after 10 clock cycles or something, it can give the like data, and it will give the R valid high, right? So without R valid, you don't know when the data is correct, right? Because you are going to get like different, the R data might keep changing and you don't know when like it's valid. So then like whenever the subordinate responds, like it will give the R valid high. So that way you are not depending on latency, you are depending on this valid signal. Okay. All right. So the next one. Okay. So the next one is the read request can fail. So in the SRAM, we assume that read request will always succeed, right? So you're asking for some data, it will always give you some data, and like you're assuming that, I mean, it will give data. So because SRAM is like a very simple, like a macro block, right? Very simple IP. But in general SoC, like I mean, your subordinate can be some GPU, or some subordinate can be some say UART or something, or like I mean some IO module or whatever, right? And then like I mean, you ask for some data, like something, and the subordinate may not be able to get that for you, right? It may fail for whatever reason. And if it fails, then like I mean, there should be a way to tell that it has failed, right? You can't continue by assuming it's passed, right? So what do you do? So now, I mean, you have one more channel here, that is RREST. The one more signal here, RREST. So this is the read response. So if the read response is 0, then it means it's okay, right? So that means it has passed. If it's not 0, then you have like different failure cases. Okay. All right. So similarly, the write request can fail. But now the problem is like if you look at the write request, now this is all going towards the subordinate. Okay. from manager to subordinate. So this is going from manager to subordinate. This is going from manager to subordinate. Nothing is coming back from the subordinate, right? So you can't like here, like because the data is coming from subordinate, you can append whether it worked or not over here. But here, nothing is coming back from subordinate. So you need a one more new channel to do this. Okay. So you need a separate channel, and this is the B channel, B response, right? So this is called the write response channel. So you write something, and after some time, or like either one clock or whatever, or after whatever number of clocks, now the subordinate can give you a response. And if that is zero, then like basically it succeeded, right? And how do you know it is actually giving the response? For that, you need to have valid as well, right? For that. Okay. So next one. So now you have all these valid and ready, like valid all these things. And now you also need, if you want to decouple the channels, if you want to improve timing and everything. So you need like the ready sync. So give like back pressure, right? So the idea is like basically now what if the subordinate cannot accept any more requests, right? So this is the AR and AW are the request channels. So if the subordinate cannot accept any request, then the ready will be down. It will keep the ready down. So now you know that okay, like subordinate can't take request, you will just hold the date. Okay, you will hold the address in the bus. So similarly, it's the same for this. Okay, and the same for this and all. So that way, like you have the ready channel as well. So like to have this to get some like back pressure. Okay, and all right. So now all of this together, they form the 5 channels of Axie. Okay. So let me clear the drawings. Yeah. So you have 5 channels of Axie. That is AR is the read request channel, R is the read data channel, AW is the write request channel, W is the write data channel, and V is the write response channel. So you have 5 channels in Axie. So these are some of the like the probably the most important signals, but then you have like a ton of other signals, extra stuff in addition to these. Like these are, but they are also part of these channels. So like these are, if you know the channels, then you're done, right? Mostly. Okay. So right. Let me see. Okay. So basically, what do you have here? Okay. So another key part of important part of Axie is basically you have 5 channels, and the 5 channels are independent. Okay. So what does that mean? So the independent means like the now you're like if you're writing a write request, your data can come before address. So you can first send the data and then send the address if you want, right? So yeah, and you can send address and then send data. So these are like as independent as possible, right? But then you have some dependency that is like the subordinate should not give this like read data or something before the address, because that can't happen, right? You need to get an address to give a data causality. But like other than that, like these 5 channels are independent. Why? Okay. So they kept independent because like in a big SoC, okay, you're going to have a ton of modules. So you're going to have like one CPU, right? So the CPU will probably have like one master port or something. Okay, one manager port over here. Maybe it can have multiple manager ports, whatever. So this is the CPU, and then you might have like a GPU or something, and say maybe like some particular, I don't know, like an NPU or something, NPU. So all of them will have a manager port, right? So I will put them as like this, okay, manager port. And then you also have like a bunch of subordinates, right? So let's say you're like some memory, SRAM or something. SRAM is a subordinate, okay? And then usually like, the GPU also might have a subordinate port, right? Why? For configuration. So that way the CPU can talk to GPU, right? So similarly, the NPU also will have a subordinate port for configuration, right? So you might have like some IO modules. Okay, UART or like SPIE or like PCIe or whatever. So all of them will have your subordinate ports, right? So all of this will be connected through interconnects. So all this goes in and goes in and out like that, right? So now the thing is like once you put this together into one chip, Okay, once you put like, I mean, these are all connected, right? So let's say like this, something like that, all connected. And you put this together into one big chip, okay? And let's say you send it to the PD team or something, and then like when they do the physical design, they find, okay, there's a long path from all the way from here to here, okay? Specifically in the address channel, okay, AW channel of this. There's a long path, right? And that is affecting your frequency, and like you can't meet the time. Okay. So now what do you do? Like, I mean, it's now it's pretty simple. Like the solution is basically you put the buffer in the AW channel, right? So over here in the AW channel, you can put a buffer, a skip buffer. Okay. So you can put a skip buffer. So by putting a skip buffer, you are basically breaking this ready path and valid path and address path and all of it, right? So you are registering them. And once you do that, now if you put a buffer here, now your path short, your long path has become a short path. So now your signal goes here, and in the next cycle goes there, right? Now, if you do this, but then like you don't have to put a buffer in the right channel, right? So the right channel might go like this, and the right channel might not have a problem. So if it doesn't have a problem, you don't have to put a buffer, right? So for the right channel, you don't have to put a buffer. So then what happens? So let me draw it without the buffer like this. Okay. So because you don't have a buffer in the right channel, now let's say your CPU gives the write and basically it gives the data as well as the request in the same clock cycle. Okay. But then when it comes to the GPU, this your data will come before your request, right? And that is completely fine according to the access standard. So the standard is written because of to handle this kind of situations. So that way you can pipeline each of these 5 channels independently. You can put registers, skip buffers into the 5 channels independently. So that way, like, I mean, you are not affecting any of them. Like, I mean, you are not causing, they don't have interdependency in that case. Okay, right. So there's a question, although Axie Lite defines 5 independent channels, isn't there an implicit dependency between AW, W, and B? How is this dependency enforced internally without violating channel independence? Okay, so the only dependency you have is sort of this B should come after AW and W, right? And that is very obvious because like now, whoever is your the GPU is your subordinate and CPU is the manager in this case, let's say. Now the GPU will not respond without getting both AW and W, right? So to have the B response, you need to have like both request as well as the write data, right? So GPU will wait for all of that and then give like a B. So which means there is no way this B can come before all of that to the CPU, right? So that is the dependency that is specified in the HC protocol, right? So other than that, is W and AW, they are independent. So any of them can come first. Okay, that's not a problem. And the other one is like, I mean, B is pretty logical, right? So that is automatically like, I mean, you can't break that even if you try, unless you have like a faulty subordinate which just gives like a B response. Then it's like actually faulty. Okay. So let's take a moment. I'll give a minute or something. Just go through all of this and like see if you understand like the 5 channels and the reasoning why the channels are like that. Okay. And if you have any questions, ask and like I'll keep answering. Okay. So there's another question. If we send consecutive read request, but the first read request fails and the second read request returns the data, how do we decide the return data is for the second request? Okay, that's a very good question. So, and the way that the what in actually like works is basically you actually can do this in the sense it's like a full performance bus. So you can actually have outstanding transactions, right? So you can keep sending requests again and again and again and again. Okay, as long as your subordinate is accepting. Okay, so if the AR ready keeps staying high, you can just keep sending requests, as many requests as you want without getting any response. And then later on, the subordinate can take all your stuff and like basically respond and it can even actually like respond out of order. Okay, so that is like based on the ID. That's some we will talk about it later. But okay, so basically, I mean, you can do this. So the question is basically, if the first request fails, how do we know, like, I mean, that failed? So how do we know which data corresponds to which request? Okay, so the spec says that for every request, there's a response. There should be a response, right? And they should be like, I mean, if you set the ID as the same ID, all of them, then the responses should be in order. Okay, so which means like for the first request, there should be the first response. Second request, there should be a second response. So you know whether the data response is valid or not from your RESP. Okay, so if the RESP is not zero, okay, that's if that is not okay, then you know, like, I mean, for that particular request, the response has failed. So that request has failed. But then the next response that you get from the subordinate might have like valid data. And for that, like the RS might be zero. And if it is zero, you know that's a valid data. Okay. That means like that's a valid response. Okay. So the point is like it will keep the valid high. Okay. Even when the response has failed, it will keep the valid high to tell that it is actually giving you a response. But then in the R response, it will tell you that okay, that response is not like a not what you asked for, that it has failed. That's why you have two of these. Okay, so take a moment and go through it very carefully and like see if you have any questions. All right. So is everyone is okay? Any questions? Oh yeah. So there's a question. Will you upload the recording video in YouTube in the channel SkillSurf? Yes, we will. So Kitmin has shared like a Google Drive link. So and you can get the recordings, yesterday's recording and today's recording as well after this finishes. So you can get that from the Drive link. And let me know like if you haven't got the Drive link, so I can like send to you again. But yeah, and then like by next week or something, we will put it on the our YouTube channel. All right. So yeah. Mm, okay, you don't have a Drive link. Can you message me? Like, do you have our number or whatever? Okay, maybe just send me your email address. Like I will send you stuff. Okay. Yeah. If anyone doesn't have like the Drive link, if you didn't get the Drive link, send your email address in the chat. We'll send you. Right. Okay. So let's move on to full axis. Okay. So this is the XC Lite. Okay. So XC Lite is a low performance bus in the sense like it is usually used for configuration, right? So where you basically write say one value, one register at a time. So something like that. Oh yeah, yes, we will share the slides as well. Okay. So yeah. So XC Lite is used for configuration. It's for what writing like maybe one or two registers and reading one or two registers, stuff like that. But XC is like a full performance bus where like you can read like a lot of things at once. Okay. So that is the key difference, right? So we'll look at this. Okay. So first of all, actually, Lite is low performance and used for register read writes. And this RRESP and BRESP, they are optional. Okay, so that's why I put them in like purple. Okay, so they are like by the standard, they are optional. So which means like you what if you are writing a Lite subordinate, you can omit them. Okay, so because it's a configuration register, you always assume that it has succeeded or something, right? Whenever you do that. Okay. And the data width is like only 32 or 64. That is the width of the bus. Okay. So by the standard. All right. So, and if you look at axis, full axis, right? So full axis, the main difference between axis light and full axis is that the burst, right? So it is used to read and write large amount of data efficiently. Okay. So what is the idea? So the idea is like, let's say you are a CPU, like, I mean, you are the manager or like, I mean, CPU or a DMA or something, right? And if you want to fetch some data from the memory, okay. So if you are only using actually Lite or like, I mean, if you are using SRAM protocol or something, then you will be just right. I mean, you will be asking every address, right? Okay. So yeah, we'll send you the recording and slides as well. All right. So we will be basically if you are a CPU or like a BMA or something, then you will be basically giving every address. Okay, if you're using Lite, if you're giving every address, and then you will get the corresponding data, right? So if you want to read like a 10 bytes from somewhere, you will get like addresses 1000 or something, then 1001, 1002, 1003, 1004, like that, 1010. You will keep asking and you will get like maybe one byte to one not byte, one inch or something, okay, 32 bits or something from the day memory. So then like that is very inefficient. So why? Because now you're like, I mean, your bus will have like a lot of activity, and if you are sharing this bus with a lot of other people, then like, I mean, so other IPs can't use the bus, and like you have like a bunch of problems, right? So, and you don't want to be doing this counting anyway. So to solve this, you have the burst, right? So this is the key feature of full axis, right? Burst. So the burst protocol, what it does is like it has like two things. So that is the AW and AR length and AW AR burst. Okay. So there's also like AW AR size. So AR size. Okay. So these three are basically part of the request channel. So what is a request channel? That is the AW OAR. This is the request channels. So they are part of the request channel. They are signals part of the request channel. So what you do is basically now, first of all, this size tells you how how many bytes of the bus you can use, right? So your bus might be like say 128 bytes wide or something. Okay, 128 bytes wide. Then by using this size, you can restrict that to like a smaller, something smaller. Okay, but I mean that's called a narrow burst. But I mean you don't usually do that. But then I mean like there is a feature in XC, right? Okay, but let's say you do that, and then now you have narrowed down this burst to you have narrowed your parallel bus, so you can basically you have 128 bytes in parallel, but you have told that you are only going to use say 32 or something out of it, right? And then the next one is like the length. So the length is how many beats, so how many clock cycles. Okay, so how many clock cycles you are going to use. Okay, so that is the length. Okay, so this one. All right. So that is, it can be 1 to 16. And you can have like, yeah. So you can have what, like varying lengths. So that both together will form your entire burst, right? And you can have the third one is like the burst mode. Okay, what's kind, so this is the amount of data that you are going to receive. You're asking for. This is the amount of data you are going to ask for. So that is basically like this into this. Okay, this is the total amount of data, right? And then you have the burst. So the burst type. So the burst type, you can have three types of burst. So the first burst type is fixed. Okay. So fixed means like you're basically giving an address, right? So the AW channel, or AR channel, you're going to give an address. Okay. So you're going to give an address, and you're going to give a valid, okay, to say that it's valid. And then the same time, you're also going to give a len, and you're going to give a size, and you're going to give yes, a burst type. So all of this is one clock cycle. Okay, so your request channel is one clock. Okay, so all of your requests will be in one clock, right? Everything is parallel. Okay, so now when you do that, what happens? Like now you are only giving one address here. So this burst type tells the subordinate how to interpret this address, right? So if you're asking for a fixed burst, so if you set the burst to 0, 0, 0, so it means you're asking for a fixed burst. So if it is a fixed burst, that means you're asking this much data, right? This into this much data. So yeah, this size is not exactly like size is, I think, 2 to the power size or something. Okay. But then again, like it's correspond to the size. So this into this is your whole data. And then within this whole data, the subordinate will respond by like reading from the same address again and again. Okay. So it will take the same address here and it will read it that many times. So if this product is say 1024, okay. So let's say this your transfer size is 1024. So now you will be reading 1024 like bytes or like words from this same address again and again. So why is it useful? It's useful if you have some in that address, if you have a FIFO or something, right? So a FIFO will have like a lot of data inside, but it will have only one port as the output. And let's say you connect that one port to that one address. Okay. So that way you read it once, you're going to get one data. You read again, you're going to get a different data. So you read it again, you're going to get a different data. So that way you read like 1024 times, you will basically read all the data out. Okay. So that is the so if you want to empty a FIFO or something, like I mean you can do that. So FIFO doesn't have an address interface, right? Okay. So that is one one way of doing it. And I think you can probably do it for stream protocols as well. So if you want to directly connect your stream to some manager or something, then the manager will basically try to read from the stream. Okay. And then like that way you can actually empty the string. Okay. So that's one way of doing that. But okay. So this is the most common stuff. Inc that is like increment. Okay. So increment means you start with that address. Okay. And then you will increment to the next address, then increment to the next address like that. Okay. And you will read for like the whole like 1024 like bytes or 1000 like words or something. Right. So whatever you want. And this has like a pretty complex scheme on like how exactly these bytes what address is implemented. Okay. So I will not like go over this here. You can check that in the spec. Okay. And unless you are writing a subordinate or master yourself, you don't need to like sort of like go into the details. Okay. But the general idea is basically you start with a base address and you increment it in certain increments to get this much of data, right? So and so why is it useful? So this is useful to read from DRAM, right? So if you are reading from DRAM or some any kind of memory, and you don't want to sort of like you want to read consecutive values. Okay. So if you want to read consecutive values, then you don't have to manually increment and give. You just give one address and you tell the amount of data, and your subordinate will do the increment and will give you all the data you want. Okay. So that is one, the most common one. And the idea is like, I mean, especially if you are reading from off-chip memory. Okay. So if you are reading from DRAM off-chip memory, then like the off-chip memory is usually very slow, right? So, and not only it's slow, it is also much slower if you read from random places, right? So sometimes, so usually you want to read in a consecutive set of values, right? So then you basically do this, and then like, I mean, it will have like a latency, big latency from like 16 clocks or whatever, or even more. And after that many clocks, it will give you all the data at once. Okay. So it will basically give you all the following 1024 bytes from that address. Okay. So that way you don't have to ask again and again, and that your latency, you don't have to spend that much latency for every request. You ask only one request with one 16 blocks latency, you will get all the data. Okay. So this is the most common incrementing burst. And the other one is like rep burst, right? So this rep burst is used for cache and stuff. So basically, like the idea is like what it finds something called the aligned addresses. So based on your size and length, and then like if you ask for, let's say, your address is aligned to this address, let's say, and you ask for this data, this address. So this is what you ask in your request, right? Then what it will do is basically it will increment like this, okay? And this is your next alignment, okay? So, and it will go here, and then it will actually come all the way back here. And from here, it will read like this and come to your place, okay? So to whatever you have asked, they will read this much. So you're reading about this much data. So what is this alignment? So this alignment is usually this size into length. Okay. So it's usually size into length. Okay. So the idea is, I mean, you can ask something in the middle, and it will start from here and will go all the way back. So usually this is used to read from cache. Okay. So cache lines. So the idea is basically, I mean, if you have a cache line, and now usually you have this entire cache line as one sort of like a location. So, and if you ask from here, and then basically, now if you're asking for this particular data, now the subordinate can, like the what it can do is you are basically asking for this entire cache line, right? So if you ask for this entire cache line, the subordinate can start giving the data from here, but then you are interested in this data more important. Okay. So then what you can do is you have to wait until you go to that data. So instead of that, you start from that data and you go and you sort of wrap around and you come back to that location. So you're reading an entire cache line at once, right? So that is the common use case for wrap. Okay. And then you have some other stuff like atomic. This is in XC5, I think. And then you have cache, and then you have security protection level. So you have like some advanced stuff. But the general idea is like, I mean, XC is mainly for burst, and this increment burst is the most common burst. Okay. So, and that way, like you will, like basically you asked only, your request is only one clock cycle, but for every request, your response can be like multiple clock cycles. The length number of clock cycles, right? Length number of clock cycles. So that's ideal. Okay. Questions? All right. So yeah, let's continue. Okay. So the bus protocol and the ports. Okay. So let's look at what are these. Um, could you please explain how XC wrap is used in caches? Okay. So the general idea is sort of like mm, okay. So the general idea is basically if you want to read like an entire cache line, okay. So the cache line is limited. Like basically you have. It doesn't start at like say I don't know like 35 the address say 0035 or something, right? So it always starts at like very like 2 to the power numbers, so like in a fixed portions, right? So now you can set this what size and length in a way that the size into length can be your cache line. So size into length can be your cache line. So that way you are actually asking for the entire cache line at once, right? But then like it also might be the case that you don't want to start from the very first one. So it's like you actually want some data in the middle of the cache line, like first or immediately, right? So if that is the case, then you basically ask for the address of this and you just say like you want a rep burst. So then what your subordinate will do is it will give you this data first and we'll get next one, next one, next one, next one, next one like this. Okay. And then you wrap around here and you go like this and you give this data last. Okay. So that's the general idea. Okay. So if you want to know more about the exact addressing schemes, you can check the spec here. So let me see this. Okay. So this is like a pseudo code for your actual transfers. Okay. So this one you can see like lower byte, upper byte, and you have how these things are calculated. Okay. Burst address. Okay. Right. So I can send you. It's there in the slides. So we'll send you the slides. Okay. All right. So the next one is basically bus protocol and ports. So what is the difference between these things? Like what is a bus, what is a protocol, and what's a port? Okay. How can I find these slides? We will put it in the drive link today. Okay. All right. So we will see. Okay. So all right. So what is a bus? A bus is basically a set of wires, okay, and a well-defined protocol, right? So so set of wires means you have valid, ready, and like a data, like a set of wires, and then you have like all these what burst and like all these different wires, right? So and then a well-defined protocol. So the well-defined protocol basically tells stuff like now when valid and ready are high, then the data is accepted. Okay, so that is the protocol. And similarly, when ready is down, then you have to keep valid and data high. Or we have to keep valid high and we have to keep the data as is without changing. So that is the protocol, right? So the behavior, right? So these wires and behavior, they both together. They are called the bus. Okay. So axis stream, and axis light, they are buses. Okay. So they are the most popular buses used in SoCs. Like in so like they were what set by ARM. So initially, and then like they are used in all the ARM anything that ARM CPU, like in anything that has an ARM CPU, right? So which is all the Apple laptops now, and all the Apple phones and iPhone, like Android phones, and then like you have FPGAs. So like Xilinx also adapted that, and so like all the FPGAs you have XE protocol, right? So XE is like sort of the used everywhere as a system bus protocol. Okay. And then the other companies also they have something that is similar to XE. So like so sometimes they simplify XE into some, they remove some wires, but the general idea is like same as XE. So if you understand XE very well, then like I mean you'll be easily, it'll be very easy for you to understand other stuff. Okay. All right. So, and like having this set of standard wires and standard protocol that helps us to create these subsystems. So you can create GPUs, NPUs, systolic arrays, registers. You can like, I mean, whatever you want, right? And like if you're designing your own stuff, you can create them, and you can connect this with other people's designs, right? So, and this is what sort of like this is why they created these buses. This is why ARM created this. So, like these big companies, Qualcomm and all, they are also able to sort of like put these chips together by buying other people's IPs, other companies' IPs, right? So the modem will be designed by Qualcomm, and Samsung will buy that modem, and the modem might have an XC port, and they will put it in their own SoC. Okay. So similarly, like I mean, some company might design an NPU, you buy and put it in your SoC. So the companies do this all the time. Okay. So, and that is possible only because of having this common bus. But then in our use case, that is you and me, it is very useful for us also. Why? Because like now there is a good open source ecosystem of many, actually multiple ecosystems. So you have multiple repositories which have actually components. So you can take any of those and you can put in your design. So as I told you at the beginning, you don't have to build all of this from scratch if you are building a full system. You can only build your own accelerator, own um, say own systolic array, own accelerator, whatever, and then you can take other people's DMAs, other people's interconnects, and like for free from the internet, and you can quickly put everything together and put it on FPGA, or else you can put it on as a ASIC or something. Right. So that is why, like I mean, this is like very convenient for us. Okay. So what is a port? So a port is basically you have what now if you are making a module, then the module might have an interface. So port or interface, right? So that is like now axis is the bus, and like you either have a manager or a subordinate. Okay. So if you are building something like a CPU or something, if you want to control other people's stuff, then you will have a manager port. Okay. Or else if you want to have some stuff like, I mean, if the CPU wants to control your IP, then you need to have a subordinate, right? Okay. So manager subordinate. So a modular subsystem, you can have multiple manager and multiple subordinate ports. Okay. So for an example, if you take a GPU, it will be a subordinate to the CPU. Okay. So if you have a GPU or a systolic array or something, then it will be act as a subordinate, and it will act as a manager to the memory. So this is what we also have in our example. So in our systolic array example, we have, so this is our systolic array. And for this, you have uh, a subordinate port using through which we are doing configuration. And then you have actually 4 manager ports through which you are requesting data. Manager ports. Okay. So basically, the CPU talks to you through this. CPU talks to this. CPU becomes a manager for your subordinate. And now all of this will go to the memory. Okay. All right. So yeah. So now the key important thing here is like XC is a point-to-point bus. Okay. So which means like what you can't basically share like one bus with many masters or subordinates easily. Like, I mean, you do that through an interconnect, which we'll talk next. But other than that, if you take one bus or like a set of wires, this set of wires will be driven by one person, one module. And so in this case, this like what some of the wires will be like basically your read request wires. So say AW address and AW say what valid will be driven by CPU and it will be observed by your systolic array, right? And then like the AW ready will be driven by the systolic array and it will be observed by the CPU. So it's a point-to-point bus. So it basically it connects 2 points, this point and this point. So you can't connect multiple points with the same line, same wire or something, right? So yeah, so this is a common like a sort of a misconception if you haven't heard of a bus before. So like if you have only looked at like network buses or something. So there's something I had like when I started learning about this. So this is not like a network bus where like multiple like things can like talk in the same line or something. So it's more like I mean it's always a point-to-point bus. Okay, all right. Any questions here? Okay. So, all right. So the next one is like memory mapped registers. So we will see how basically the CPU talks to all the GPU, like NPU and like USB and Wi-Fi. Okay. So the way this works is like each subsystem will have a set of registers. Okay. So how does the CPU actually control all these things? So like how does the CPU command something like to be done by the GPU, right? So or the NPU. So the way this works, you like GPU and NPU will have some registers inside them. Okay, like this. So the GPU has like start done status and NPU has like start done status, and like USB might have data, Wi-Fi might have data, something like that, right? So and CPU can basically write to them, and that way CPU can set the parameters and it can start the subsystems. So it can basically give a job to do, right? It will set the parameters for the job and it can do clicks right to the start register, and the GPU will take that as a signal to start doing stuff, right? And similarly, CPU can read from these registers. It can read the state of the register to see if the GPU has finished processing, or else like it can see if GPU has failed. And if it failed, then you can see some other registers to see what is the failing case, right? Why it's failed and what is the error and all that. So you can, so basically the way that CPU and GPU talk to each other, or the CPU and NPU talk to each other, is by reading and writing to these common registers inside these modules. Okay, so these are called memory mapped registers. So the CPU usually has like one manager port, right? So I mean, some might have like more than one, but then I mean, let's assume it has one manager port. So and from this one manager port, how do you control all these multiple subsystems, right? So to do that, you memory map all of them to one memory space. Okay. So, and this is how we do that. So basically the idea is you have a common memory space for the entire like, okay. So the CPU sees like a very large memory space, right? And the CPU can basically read and write to any of those memory like locations. Okay. And inside each of your GPU, NPU, USB or whatever, inside that you have a few registers. Okay, so 0, 1, 2 and 0, 1, 2 and like basically your small registers with like small addresses, right? So now the way we do this is like they get mapped to this big address like this. So they get mapped through the interconnects, okay? And yeah, so they get mapped through the interconnects. So what an interconnect does is basically an interconnect. So like, let me see if I have a diagram for that. Yeah. So over here. Okay. So one of the jobs of the interconnect is to basically map all this what status registers into this one space, right? So the CPU, if the CPU wants to talk to the NPU, what it will do is it will write to say this 201. Okay, I mean, or else read from 201 to see if the NPU is done, right? So the CPU will give a at read request from 201. Okay, so the interconnect will see, okay, the address 200, what you have is an NPU, right? So then it will subtract the 200 and it will basically it will give the address 1 to this particular um, like subordinate. So inside here. So and inside here at 1 you have done, right? So you will read this done value and put it in the bus, and that will be sent to the CPU, and the CPU will look at that, right? So this is how you are able to read and write into like any particular subordinate, and you can actually read wherever you want. You can read GPU, or you can read like USB, or you can read and write Wi-Fi, whatever you want. Okay, so that is memory mapping. So, and the other way is like now all of these GPU, NPU, and everyone like CPU and NPU, they all act as like managers to the memory, right? So how do you connect all of them to one subordinate? And again, you use interface. Okay, so this is how they are like wired together physically. So yeah, so what you do is basically you use an axis interconnect. So as I told you, axis bus is always point to point, right? So you have only one master, one manager for per bus. Okay. So this is one and this is one and like that. Okay. So to connect all these multiple subordinates to the same manager, okay, what do is you put this interconnect in middle. Okay. So this interconnect will connect multiple subordinates to one manager. So how does it do that? It acts as for every subordinate, it will act as its own manager, right? And then as like on the CPU side, it will act as like one subordinate. Okay. So the CPU thinks that there is only one subordinate out there. Okay. And it will be giving all its requests to that one subordinate. And now the axis interconnect will basically distribute this to all the different subordinates and collect their responses, put them together and give it to the CPU. Okay. So the interconnect does this orchestration. Okay. All right. So similarly, now when you have multiple managers and one subordinate, so you have one common memory, one common DDR, and the common DDR will have only one port, right? And this one port will be mapped to multiple managers. So you have like this GPU, NPU, and like all of them, and all of them are connected through the this interconnect. So the interconnect acts as a subordinate to all of them. So it takes everybody's requests and then it lines them up and it sends it to the like memory, gets the data, and it keeps track on who asked what, and then it will give the data to that particular manager. Okay, so that's what an interconnect does. Okay, yeah. So the interconnect also does like address translation. So that's what I told previously. So it knows like which, I mean, if you ask for 201, it knows it's done. This done port of NPU. So it will send that request to NPU. Okay, that's that. And okay, so the next one is hierarchical interconnects are possible. So what does that mean? So that means like you actually can put an interconnect together, and now you can wrap this into one IP if you want all of this into one IP. So this one IP will have a subnet. So and then what you can do is basically you can have some design like this. So you have a CPU. The CPU will have one manager port, and you have a multiple subordinate ports. So you have one manager port, and the interconnect will have multiple subordinate ports like this. Okay, and then this will go to another interconnect here, and that interconnect will have multiple ports. So that's what we have done here as well. right? So the CPU has multiple. Okay, so it's a first interconnect, and then that becomes a manager to the other interconnect. Okay, so and that interconnect goes to the memory. So this way, like you are able to, you can stack multiple interconnects together, and this way you basically there these are layers of abstraction, right? So the memory only sees one manager, okay, and the CPU only sees one subordinate, and in the middle you have all of these different things. So again, this makes the complexity possible, right? So this is what makes the modern SoCs, modern like chips possible, because like whoever is designing the CPU doesn't have to think too much about having supporting different GPUs, different NPUs, and like different memories and stuff like that. They only have to make like one or two few master ports, and whoever is designing the memory just need to have one subordinate port, and they have to just basically make it as fast as possible, right? And this way, you basically it's like building blocks. You put everything together, and because the protocol is an open protocol, accessible to everybody and everything. Now you can put all this together, and you can make a system easily. Okay. Otherwise, you have to write all of this yourself, so which you don't have to do. Okay. Right. Yeah. So if you are writing an NPU, then what you do is basically you will, yeah, if you are writing an NPU, then what you will do is that you will be writing only your own configuration registers. Okay. So the start, done, status, you will only do those things. You don't have to write anything else, right? So, and you don't have to worry about like what your address is going to be and like all of that. Okay. So in general. So yeah, and that will be done by the integration people. So who map these addresses and do stuff. Okay. And the integration team will put everything together. Any questions? Could you please cover memory interface generators later in the lecture or a convenient time? Are you asking about SRAM generator, or else are you asking about um, like this software or something that basically creates this maps for you? This like these things, and it will create the ports and stuff for you. Which one are you asking about? Okay, so you want to basically know like I mean how to interface your IP to DDR, right? So if you are I mean if you are doing that, then basically I mean what you can't directly unless you are working at a company which does that. Okay, so you won't be directly talking to DDR. So the what like your SoC, whatever the SoC you are using, will have like some sort of a like a thing that talks to the DDR, like either sort of a DMA, something that talks to DDR, and you will be talking to that, right? So and that will depend on like every single SoC or every single design, right? So like for an example, in Xilinx FPGAs, you basically, I mean, you have a common like memory port where you can just talk to that, and you basically talk to the Zing PS. In some most of the boards, you talk to the processing system. So and the processing system will talk to the DDR for you, right? So and there will be like some maxi port somewhere, like in if your SoC is XE, to which you can talk to as a DDR. So I will not be covering that, but we will be covering an example where we interface our systolic to the memory, okay, through like a bunch of connections. So you can probably get some idea from that. Okay. So this basically differs from every use case to use case. Any other questions? Okay, so let's move on. Okay, so now let's look at some XC IPs which you can get from open source and the open source repos. Okay, so these are some examples. So basically, so these are the stuff that might be most useful for you. So one is like XCDMA, right? So what is a DMA? A DMA basically bridges um, stream to a full XC port, or else vice versa, or else it bridges like a full XC port to a stream, right? So the idea is like, let's say you have, in our case, we have a systolic array, and the systolic array will be giving an output, okay? Will be giving an output stream, and you have to basically take that stream and you have to write it somewhere in the memory, right? So you have to write it somewhere in the your DDR. Okay. So your systolic array gives a stream, and you have to take the stream and write it somewhere in DDR. So that is what the DMA does. Okay. So now this is a S2MM. So it's a write DMA. Now, like you need some information, like where do you write this? Okay. So where do you write this? Like, I mean, you get a stream of data, and the question is where in the DDR should you put the data, right? So that is given through the descriptor. Okay. So that is through the descriptor port. So the descriptor port, it differs from DMA to DMA. So sometimes it can be access stream. So that is what we use, like in our example repo. So or else it can be actually light. So that is what Xilinx uses in their DMA, right? Like that is like if you are in Vivado, if you are using the block diagram, or else like Xilinx IPs, then you have an actually light port. So this from the Vivado, right? So this is from Vivado, and you can see this is the descriptor port, okay, and then this is the stream port, okay, and this is the this is the stream port, and this is this port. What is that? Full XC port, okay. All right. So this So what do you have in this descriptor? So descriptor is usually like, I mean, mainly two things. So that is the base address in bytes. Okay. So the question is like in the DDR, where do you put it? Okay, what location? Okay. So what is in which location do you put that? And how many bytes do you put there? Okay. So how many bytes do you put there? So those are the two variables, and those are given through this descriptor. Okay. And that way, like basically the DMA knows to start and basically copy all this data to that location. So now this is a write DMA. So similarly, you can have a read DMA. So this is a read DMA, MM2S, a memory map to stream, right? So what this does is like it has a manager port which reads from the DDR. Okay, it reads from a given base address, certain number of bytes. You read it from there, and you give that as a stream on this side. Okay, so this is how we get the data into the systolic array, right? So you have to get like your input matrix and like your weights matrix and all those things. So you get that through like as a stream from a DMA. Okay, and again, like I mean, you for the descriptor, you actually tell it basically how many what bytes and what is the location. So and it can be access stream. That's what we use, and in Xilinx it will be actually light. Okay. Okay. Any question about like the general idea of DMA? Okay, so I think I can tell you like why we are not using Xilinx DMAs as well. Okay, so I mean, so I was using them previously, but then you have a bunch of problems. So like first one is like the most obvious one is like sort of if you use Xilinx, you can't use anything else, right? So in the sense, this is property of Xilinx. So if you're only putting your design in the FPGA, you can use this. But then if you want to simulate this using Verilator, or else like, I mean, if you want, I don't think there's a way. So, and or else like if you want to maybe do connect with IDEX, okay, or else you want to connect your design with something else, like say you want to do a tape out or something like that, ASIC, then you can't use the Xilinx DMA, right? Obviously. So that is one limitation. And the most important limitation is that the Xilinx DMA is designed to be simply drag and drop and like just connect these wires and get it working with the example, but not for actual performance or like, I mean, fine control, right? So what does it mean? So it means that like Xilinx DMA has this actually light port, right? So you can write into these configuration registers and then it will basically start and it will do stuff. Okay. So, and writing into this configuration registers, like this actually light has a certain latency. So you need to have like certain number of 15 clocks or like a few clocks, probably not 15, but maybe some clocks it will take to write into this light. And after writing only, like the DMA will start sending requests to collect data from the what DDR and everything, right? So, and once you collect data and everything, and now you have to keep asking this again and again and again from the CPU, right? So from the CPU, you have to keep asking, are you done? Are you done? And then like if you are done, then you have to write the new address, right? So now by doing this, you can't like basically now you can't give the next address immediately. So and there is, I mean, you probably can, but it's not hard, right? So especially from the CPU, and or else you can actually control this from your own module if you want, but then you have to write sort of like an XC Lite manager, and which we didn't want to do, and that is even more complicated. So yeah, so if you know like, I mean, what is the how you are going to increment like this access stream, like or else how you are going to implement your addresses, how which addresses you want and everything. And if you know this from the TL side, from the Verilog side, if you have your own modules which can do that, then I mean it's much easier to sort of like use access free import. So that way you can keep giving data as soon as like you can. So and the third one is basically the resources. So the access we found that the Xilinx DMA takes more resources than like the open source one. Okay. So it is basically there as a sort of like a first, I mean, for to help the beginners. So you can put stuff together and easily get it working, right? So that's the purpose of access to this one. And then it is also like, I mean, inconvenient because like you have to generate this DMA from tickle scripts. So you can't generate it from Verilog. I don't know if there's a way, but you can't generate it from Verilog. So you have to write tickle scripts separately, which I have done that before. But then you have to keep those tickle scripts correct and like all of that. So which is it's a bit of a pain to work with this DMA. So instead of that, like we just got the open source one, and you put the open source one inside, and you connect everything in Verilog. So and then that way you have connected all the stuff, and you can control this descriptor also from Verilog. You can write, you can give your addresses and let the DMA do the stuff. Okay. So and the other thing is like it is much more performant because it can prefetch data. Okay. So what does it mean? It means like you can prefetch the descriptors. So it will take your descriptor here and will give a request to the DDR. Or like, yeah. So it will take your request and will give a read request to the DDR. And before the data comes in, you can give the next descriptor. So that way you can keep giving the descriptors and will keep giving the stuff to the DDR. So you don't have to wait until it is completely done to give the next descriptor. Okay. So that is sort of like, I mean, and that way you can sort of like uh, get some performance out of it. Okay. So these are the reasons why we use the open source DMA, because like it's very convenient and yeah. Okay. Any questions? And you can take our test bed as it is. You can take our system array design as it is, and you can replace the system array with your own design. So that way you don't have to sort of like, I mean, go through a lot of pain. And this open source DMA, it still works with Vivado. So you can get like we have put it on FPGA, it works on FPGA, and we have everything. Okay. Questions? Okay. So yeah, I guess we can continue. Okay, and the second one is like a FIFO. So there's a simple example. So you can basically first in, first out with a given depth. So let's look at some other IPs over here. Yeah. So this is the repository. Okay. So this is currently depreciated. So like if you can, I mean, if you want to do, if you want to have something safer, then you can probably look at Taxi. Okay. So he has like basically the guy who is building this, he has handed over to like I think another guy, or probably it's the same guy, but yeah, it's the same guy. So he's actually putting like a bunch of transport libraries over here. So and he's moving them to system Verilog from Verilog. So and so here you have the latest IPs here. And if you don't find the correct IP here, then you can look it up over there. Let me put it for everyone. Okay. So this is the most up-to-date one. And if you can't find it over there, then you can look it here. Okay. So yeah, and we can take a look at the IPs, and here you can see the DM, right? So XCDMA. Okay. So and the XCDMA is basically he has a read DMA and a write DMA inside. Okay, write DMA and read DMA. And if you look at the write and read, these are like separate. So you can see. Okay. So you have basically you can do like a what you can it's fully parameterized. So you can have different data widths, different address widths, and then like the strobe and everything is calculated automatically. And yeah, so you can enable all these different ports. Okay, and yeah, so here you have your descriptor input. Okay, so this is how the DMA works. So let me zoom in and yeah, so this is the descriptor port. So the descriptor port, you can see it's an XE string port. So where is it? Valid and ready. Okay, so you have a valid and ready. So it's an XE string port. And then this is the payload, right? So in the payload, you have address length. Okay, so and this basically address and length gives you the what um yeah. So you have like an insert an address and you tell how many bytes, okay, to write to that address. Okay, so how you read from that address. Okay, and then you also have a status output. If you want, you can read this, or else you can ignore it. So in our case, we are just ignoring this. And here you have your stream data. Okay, so this is a read channel. So read DMA. So which means your stream is the output. So the DMA will read from the memory and give you the string, right? So which is why you can see that T valid is an output signal. Okay. And T data is also an output signal. Okay. And you have T keep, and then you have T last, ID, destination, user, and everything. Okay. So the stream port. So this is what that comes out of the DMA. Okay. And this is what you will connect to your module. Okay. And over here, this is the XE master interface. Okay. So this looks simple because you only have the two channels of the five. Okay. So you have the address channel and you have the read channel, right? Read data channel. Okay. And you also have an enable port. Okay. So yeah, that is the whole DMA. So you can look into that. And similarly, you have your write DMA over here. And yeah, so the write DMA is pretty similar. It has the same parameters and everything, and it has the same descriptor. And the only difference is the data goes in. So your output of your module will go into the write DMA. So this is what you will connect to your module, right? So you have your input via the data is an input, and then you have keep valid, ready, last, ID, and destination and use, all of that. And this is a master. Okay, actually this is a master, and this master will be basically writing whatever the data you give to the DMA. It will be writing to the like memory or whatever, right? Okay, so this is the DMA, and yeah. Any other question? Any questions? Okay. So let's continue to, to XC test bench. So how do we test our XC design? So like once you put stuff together. So the idea is like basically we will not be but generally you will not be writing XC modules. So you can write them, like you can write an XC slave. So but then writing a full XC slave is like I think pretty challenging, right? So you can find some good posts so from zip CPU and all on how to write like a good slave, and that is very difficult because like XE has all these weird conditions, and you have to satisfy all those conditions. So the data might come first, the address might come first, and all of this, and all these different addressing modes. So you have to handle all of them. So it's actually a pretty good exercise if you can write like a good slave. But otherwise, like if you are building something else and you want to basically put stuff together, then you don't have to write it. Okay, what you do is you take other open source modules, put them together. So if you put all your modules like that, and now you have a system which has AXI ports, right? Then how do you test that system? So how do you do integration testing, right? So in that case, so we are going we'll talk about AXI test bench, right? So how do you do that? So the way you do that will be like this. Okay. So there's the standard way of doing this testing is called the AXI VIPs, right? So you can have AXI VIPs from Pulp. Okay, let me show you that as well. So yeah, so this is another one. So this is from ETH Zurich, and they have a pretty good repository of AXI modules. Okay, so and they also have their own DMAs and like all of that. So if you want to use it, you can use that. So this is one way, one like you can use this also, right? So yeah, yeah. If you want any stuff, you can use from here as well. So if you look at, they also have this VIPs. So let me see. Okay, they're here. All right, so you have a package or system verilog package, and they use like system verilog a lot. Like, so you have very nice interfaces and like very it's very beautiful what code. Okay, and you can learn a lot from by reading what the way they write stuff. Okay, so it's like really good stuff, and I use this a lot in my current project. So yeah, so they basically have this what active driver and like yeah, so there's a active light driver, and then you have an active driver. Okay, so yeah, so these are VIPs. So basically, they can drive an XC port, and they can drive random transition into an XC port. So in that way, you can test your XC port cleanly. So that is one way of doing that. But then the thing is like usually I want to do sort of like an end-to-end testing. So I want to test the firmware with it, and I want to see like basically I want to send the matrix through the XC port and like see the matrix get multiplied and comes out okay correctly. So those things it is somewhat harder to do with VIPs, right? So what I do is basically I put like some existing modules together into my own sort of XC test bench, and that's what like I'll be introducing here. But then you are free to use the VIPs as well. Okay, okay. So what I do over here is basically something like this. So let me draw. Okay, so this is our module, right? So let's say our systolic array, right? So this is our module, and this module we basically put it together with a bunch of other modules. So the first thing we do, I'll talk about that at the end. So this generates so our module has a manager port. So which means like it wants to write into memory and read from memory, DDR, right? So you have to write into DDR, read from DDR. So that's why you have a manager port. So what you do is you take this manager port and you connect this into an XP to RAM module. So what this XC to RAM module does is basically it converts XC, like it behaves like a subordinate, and on the other side it exposes an SRAM protocol, right? So SRAM is the first protocol that we saw. That is, you have like read enable, read address and read data, and write enable, write address and write data, right? So this will expose this port. So that way, like whatever the transaction comes here, like it will convert that into like it will basically do the address translation and will do all of that. Okay. So and this is something you can get from zip CPU or you can get from LX4K. So these are the IPs that I showed you, and I'll show you zip CPU as well, right? So these are the three repos. So one is zip CPU, LX4K, and the other one is like Pulp. So these three of them, they have like these XE modules, like open source, and they're like pretty good. You can take and use them. So these are available in both of these, and then you convert this XE to RAM protocol. So this way, the idea is like you don't have to worry about address translation or like I mean all these weird multiple channels and like weird dependencies and everything. Okay, the only thing you have to care about is like I mean on you will be dealing with this side. So if read enable comes, then and the read address comes, then you have to give the read data like in the next cycle. And if write enable, write address, and write data comes, you copy it into the memory. So the only thing you have to deal with is this one. Okay. So that's what we'll be doing. Okay. And then you have like your congestion. Okay. So this is you have this. Okay. And the next one is like congestion emulation. So that is what this part. Okay. So now this like this Axito RAM module is sort of full performance. So it's like you get like you don't lose any performance. You get 100% performance from XE to RAM directly mapping. So that's very good. But then the thing is like you also want to test cases where like you I mean now you have a manager and like you are interfacing with somebody's subordinate, right? So the subordinate might pull the ready down at any time or like I mean you it will have all those different issues, right? So you want to test all those cases. So how do you test those cases? You test them by putting so we put like a this con- we emulate this congestion over here. So that's what I do here. So I have this like a bunch of like logic here that basically randomizes the valid and ready signals. Okay. So by randomizing these valid and ready signals, like basically the valid will go down randomly or ready will go down randomly. So that way you can stress test your design and you make sure like I mean you don't have any dependencies. So to make sure like your design doesn't sort of assume the ready will be always high or like stuff like that. Okay. So and that's why you have this one. And yeah, and the next one is basically what now, how do you test your firmware, right? So to test your firmware, so the firmware, there's your C firmware. So from your C firmware, you basically, the idea is your C firmware runs on a CPU and the CPU controls your module, right? So the C firmware is the software code that controls your module. So you basically write into the registers, you start and stop the module, and basically you give an input at matrix and you let your module work on that matrix and you get an output and you have to check if the input and output are being put into the memory correctly and if they are matching and all of that, right? So so the question is like, how do you test it all the way from here to here? So the entire system, okay? How do you test it? So to do that, we basically connect this system verilog. So we have stuff in system verilog which handle these signals. We connect that to C through DPIC. So there's something called DPIC. We'll go through that step by step. Okay. So that's how I do that. So by connecting that through DPIC, like I can, whenever there's a read request, I can give I can call a C function, which will read the data from the memory that is in the control of the C function, right? And then whenever you want to write something, you call a function in C to write the data. So that way, like you are basically talking to the firmware as well. Okay, so this is how we do the whole end-to-end simulation. It's like an overall overview on that. Okay. So any questions in this, high-level questions before we go into this? Does our TB act as a CPU? So kind of yes. So basically the test bench will be running this C firmware. Okay. So the idea that is like, I mean, the way I do it is basically I want to test the firmware as it will run on the what on the actual hardware. Okay, so that is the way it will run on like FPGA or like on your IVEX CPU or something. Okay, so the exact same code. Okay, like in the sense, so I switch some functions, but then like basically you don't have to change any logic. So the same logic code will run like we test it in the test bench, right? So that's how I do that. Okay. So that way we can see if there's any problems with the firmware or anything in the simulation itself. Okay. So let's move on to, yeah, register files and firmware. Okay. So the question is like basically how does the firmware talk to actual your custom module, right? So I'll give like a high level picture on like basically the simplest way on like how this happens. Okay, so this is the idea. So let's do this. So now, yeah. So this is the C file. Okay, so this is what happens in C. Choose a different color. Maybe yeah, something like this. Okay, so this is what happens in C, right? In your C firmware. So you can see like, I mean, okay, what we do is like we define a base address for your stuff. That is for your, what is that? For like your own module, right? So just like previously, the GPU's configuration registers will have a base address, NPU's registers will have a base address. So similarly, we define a config base address for our own module, right? So that will be like, let's say this one. Okay, so this is C code, right? And then what we do is we basically write this as a volatile int, cast this as a volatile int. So why volatile? Because like, so the idea is like you tell the compiler that like this value can change from outside the control of the compiler. Okay. So that way, like the compiler will not try to optimize it too much. Okay. So otherwise, like if you don't put volatile, what the compiler does is if you read the same address again and again, then the compiler like will look at that when you compile the code, and it will think, okay, now what you can do is you can basically what they are reading the same thing again and again. So you can just remove the whole thing and give the same data again and again, right? So it will try to do optimization like that. So you have to tell the compiler, I mean, now this value will change from outside our control, right? It will be changed by the actual our own hardware, right? Which sits outside the CPU. So that's why you say volatile. So you cast it as a volatile, and this is how you basically read it. You write it. Okay. So you are writing into this configuration 5, you write this 123. Okay. So what does this mean? So like this is the base address. From here you add like, I mean, 0 and you have 1, 2, 3, 4. So the word we are using int. So int means 32 bits, right? So we assume the registers are say 32 bits here. Okay, like I mean, uh, they are 32 bits. So we are writing into the sixth register, right? Zeros is the first one, second, third, fourth, and the sixth register. We are writing into that. We are writing 123. And we are going to read it back again, printf. We are going to read the value, this one. Okay. So this is how you read and write into the register. Okay. So now how do you implement this register in Verilog? All right. So this register is implemented in this DMA controller.sv. Okay. So inside here, so this is like a very simplified picture of what's going on in the DMA controller. Okay. So, and this is like a style that you can use yourself for your own designs, right? So what we do is basically we define these ports. So you have the clock port, you have the reset end port, and then you have an address width, and you have W address and the read address. Okay. So these are the read address and write address. And also you have this write data and read data. Okay. So these are input ports, and this is an input port, and this is an output port, right? So the read data is an output port. Okay, right. So now the actual register is you define like this. Okay, is the logic. You have 16 registers here. Okay, so you have 16 registers, and each of them are XC data width wide. Okay, so what is XC data width is 32. Okay, so and we are using 32. Okay, so over here, so that is the int size of an int. So you have int size registers and you have 16 such registers. Okay, total. So your actual data is going to live inside this variable, like configuration registers. Okay, in Verilog. Okay. So now what you do is basically you connect this combinationally. Okay, to this. So that is the R data is equal to RF or what R address. Okay. So whenever you get an address, then the data you'll get the same data. Okay. So the reason we do this is because like we are using this XLite RAM and like to convert this, and that expects the data to be combinational, right? So that's why we do this. So yeah. And then like, I mean, when you write into that, you have like one clock latency. So you can do that. So that is what, if it is reset, then configure is 0, all that. And if the write enable is high, then into the write address, you write your write data. Okay. So here, like we are asking to write into the sixth, into 5, address 5. So this address 5 will come here and you write into the fifth. So the index 5 completion register, you will write your this particular data. So the 1, 2, 3 will go into this, into this. Okay. So that is how you write in here. Okay. So this is how you can write your, you can build your stuff, register file. So it's pretty simple. Now the question is, how do you connect this to this, right? You have this, you have that, and how do you connect them? So, and that is how you, that's what you do in this top axis, right? So top axis.v. So this is like a, okay. So what we do is our top axis.v, this has like, actually 5 axis ports. Axis ports. Okay, it has 5 axis ports, and it has one subordinate port, and it has 4 manager ports. Okay, 1 subordinate and 4 manager, and they are full axis. So the reason I'm doing this is because like I want to later on I'm putting interconnect together, right? I'm putting all of these through an interconnect. So because of that, like I mean, and I want to keep like stuff as full axis, because in Xilinx, like FPGA, if you have full axis, you can directly connect it to the sync module, right? Sync PS processing system. Otherwise, like you have to, I mean, when you connect it, it creates like its own module in the middle. So, and that differs from FPGA to FPGA, and like it makes the script more complicated. So I want to have like just one. So for this, I'm having a full axis port, even for configuration, right? But then the thing is like, how do I bridge that? So I use this axis to axle adapter from Alex Frankie, right? So this bridges an axis port to an axis light port, right? So you can see over here, this is the axis subordinate port, okay? So, and it has like a ton of signals, and all of them are connected here to the axis subordinate port. And then on the other side, you have an axis light manager port. So that is where all these signals are connected. So it basically takes it behaves as an axis subordinate, and on the other side, it behaves as an axis light manager, right? That's where we like, I mean, we take this. And then we connect this to this RAM. Okay. So that is, um, okay. So yeah, this thing comes out, and now you have an axis light manager port, and you can directly connect this axis light manager port to this. That is, you can axis light to RAM port. So this also from LX Key. Okay. So you can have, you connect this on one side, it acts as a subordinate for axis light. Okay. On the other side, it acts as a register what port. Okay. Or else like a RAM port. Okay. So this RAM or register file, either one of those. So like, I mean, so it's a simple SRAM protocol, right? So you have register write address, write data, and write strobe, write enable, and read data, read enable, and all of this. Okay. So, and you can, so this is like how many clock cycles you should wait and everything. So it has some extra functionality, but I don't want any of that. So I'm putting 0. So basically, you will get the write data pretty much immediately. The next, so the write will be done immediately in 1 clock. And then you have um, the write acknowledgement is always high. So you will always get the write acknowledgement. And the read wait is also 0. So you will get in the next, what you will get in immediately in the same clock. And the read acknowledgement is also 1. So you will get the data all the time. Okay. So I'm simplifying the word a little bit. And then, okay. So here you have your base address, right? So we have the same base address as here. So this is important. This is how you do the address mapping, right? So if you use the Vivado manager, Vivado address manager, it will do that part. But again, as I told you, you will have to write tickle scripts and everything to make it reproducible. And the tickle scripts are a bit like sort of finicky because when you go from one FPGA to another FPGA, like if you have too many things, then you have to have like too many edge cases. So we don't want that. So we do support multiple FPGAs, but then we keep the tickle script as simple as possible. So, and we don't use the like Vivaro's interconnects or anything, right? We use the open source ones. So that way, like you have the base address here, and we use it the same base address here. So I'm setting it through a macro. So that way, like I mean, both of them are same. So I have a Python script which generates the C macros and the system.log macros, and then you include them. So that way, like they will always be the same, right? So and okay, and then you have the SLI bytes. So basically the width by 8. So how many bytes, right? And over here you have now you do the basically this address translation. Okay, so the interconnect will give you this address and it will give you the full address. Okay, it will give you the whole address. And here, like we basically subtract this base address. Okay, this base address we subtracted, and then we also divide it by the number of bytes. Okay, so like okay, so we divided by the C log 2 of that. So we shift it. So basically we divide it. So the idea here is now from C, the addresses are always in bytes. Okay, so you are looking for like I mean a certain particular byte, right? So, but inside here, our this address, or else like I mean whatever we are asking here, okay, is basically the first register, second register, third register, fourth register. But each register is 32 bits or 4 bytes wide, right? So on the C side, to go from first register to the second register, you have to add the 4. Okay, so C basically if this every time you increment and call this, it will be giving 0 and 3, no, 0, 4, and it will give 8 and 12 and 16. It will give addresses like that. And you take those addresses and you put it over here. I mean, now you're going to have a problem because like this is the first register and this is the second register. So you want to change it into 0, 1, 2, 3, 4 to be read in Verilog, right? Over here. So because in C it's in bytes, in Verilog it's in words. So that's how we have designed it. Okay, you can do whatever you want. But yeah, in this particular case, we have designed that way. So to do that, what we do is we like I mean left shift this, okay, by the number of C02 of this. So by doing that, like we are basically dividing this by 2 to the power 2. So you get like basically you are dividing this by 4. So every number you get from here, you divide by 4. So that's how you get these numbers. Okay, divide by 4. So to go from here to here, and that is this part. So you subtract the base address. So from C, you will actually get this B000001 or something. Okay, and so B004, and then basically you subtract the B, and then you divide by 4, and you get 1, and that 1 you send it inside. Okay, so and this is the one that will get sent to here. So this is how we have connected this this DMA controller all the way to the what XC port of the CPU. Okay. Any questions? Okay, so I guess you understood everything. If you have questions, ask. See. Okay, so we'll quickly take a look at our DMA controller and do the full simulation, and we are done for today. Okay, so you can keep asking questions. Okay, so this is the actual DMA controller we have. Okay, so the you can see in the DMA controller we have what this is the, as I told you, like we have a register port, just like the register file. So we have a register file inside the DMA controller, right? So this is the register port that writes into that. And then we have over here, we have our, this is how the CPU writes into the data. So it's like one key part. So the thing is, like, we put this at the very end because the CPU has the priority to writing stuff. So, like in Verilog, there's a rule that the last assignment wins. So even if the RTL is writing something over here, then the CPU write should take precedence, right? So that's why we put that at the end over here. Okay. All right. So, and then we have whatever we have over here is basically using those registers to control the DMAs. Okay, let's see how that works. Okay. So you can see that now you have three ports, four ports. These are for the four different DMs. Okay, and each of them is like the same thing. So you can see each of them gets a descriptor, like each DMA gets a descriptor, and it gets a tag, and it gets valid and ready, and status and everything. Okay, so I mean we can ignore this tag and stuff, but then like we have valid and ready, and we have descriptor, right? So if you look at our actual register file, okay, so what we have is this is our address map. Okay. So like we have these three DMAs which pull the data in. So like just like the vector Mac. So in the vector Mac, we would take the K, you read X, you read A, and then you multiply everything and add everything, and you have the output, and you put the output out, right? So these three are read, and this one is write. So okay. And for each of that, you have this done address bytes and done address bytes. Okay. So this TU size extra. So that is like if you want to get any extra information, you can get from that, but we are not using it. So we have done address and bytes. We have only three, right? And now we have 16 registers like that. Okay. So, and that is CFU. So this is only for debug purposes. We are not using it. So for anything else, okay. And this is the reading part. So let's look at one of these. So this is the controller part, how the DMA is controlled. So what we do is basically, it's pretty straightforward. So we connect the address and MM2S address and the length. Okay. So they directly come from the configuration register. So the register has this address register and the bytes register. So we directly connect that to the address and length over here. And yeah, so the valid port of that basically is that whenever the start register goes high, okay. So whenever you have a start register and you have like S2MM ready, so that is the S2MM ready comes from so S2MM ready comes from this thing. So that is the output port, right? So the idea is like, I mean, if the output is plugged, then you don't send like any new data over here. So you don't send data. So when we wait for the output to come high, and then like you send the new descriptor, right? Okay. So and then you have so this is your like this is how you control this one input. So it can be X or K or something. Okay. And that's what you do for the other like for K and for X and for A. Okay. And this is the S2MM part. Okay. so which goes out. Okay. So similarly, like this valid, like we make sure, like I mean, only when you clear the what when the MM2S is ready. So that is when the K is ready. Okay, then we give the valid signal. Okay, so that way like you don't sort of overwhelm the system. All right. So and then it's pretty straightforward inside here. So the MM2 is done. So whenever you get a done like a bit from the DMA, okay, so you set this register to high, and so that way like you set each of these registers to high. Okay, and this is like all of them. Yeah. So you can see the start signal. Okay, so this is the start register. So the start register basically goes 0. So immediately, I mean, you set it to high. The PS sets it to high or 1, and then like the whole thing begins. That's how you send the first transfer, right? And then at the end, you are when you are done with everything, like basically what you set, like when all of these are ready. So that means all these packets are accepted, and as soon as they get accepted, you set the start to 0, right? So the your own hardware sets the start to 0, and from the outside, the CPU will set the start to 1 to start it again, right? So that's how you reset the start signal. Okay. So these are the done signals, and the PS can read it and get it. So in this particular example, in this particular systolic array example, we are not using the full performance of the open source DMA, right? So I've been using this setup in a different project, like it's a accelerator project, and so I wanted to extract this part away, like into something simpler, so which we can teach, and also I can use it for as like a test bed for my different modules, and people can put their own designs into it, and you can take this DMA controller as it is, and it works for different cases, and you can add more and more complexity, and you can make it more and more performant. So, like for example, to this addresses without giving these addresses one by one, you can calculate the next address as you want, and you can increment it. You can do all those things, right? So it helps you to like it. You can use it for your own stuff as you want. Okay, so this is the DMA controller, and the next one is like the full test bench and the simulation. So right. So to do the full simulation, you basically take our module. So let's see. So we will discuss the systolic array next, the actual systolic array next week. Okay, but you can start playing with that if you want. So you get it and you do this quick start. Okay, so you clone this and you do this one to get this VIP, and yeah. So you do like a make fresh, make enter. You enter the container just like I told you yesterday, and you can test make query and like make wave to test your whole simulation with systolic array, XCDMAs, and XC test bench. Okay, so it basically looks like this. So okay, so you go in here and make enter. Okay, so inside that you can do like a make query. Oh, so I think I've been editing this file. Mm, and you can see that complete. And yeah, so then you have also like you can try the IBEX test. So this will test your whole the systolic array with the IBEX CPU as well. All right. So anyone has any questions, you can ask. Yeah. So will be successful and all the output data match. Okay. All right. If you have any questions, you can ask about the whole thing, or else, yeah, and you can do. Right. Thank you. All right. So yeah, we can end the session. Thank you. Thank you so much. So see you next week.